Hi guys, today we're going to be looking at kinematics and calculus and how they could be used to calculate different values of velocity and acceleration. First, I'd like to just look at different symbols. The first we've got velocity, displacement, momentum, the net force. We've got time and acceleration, which we'll be all using today. I want to just start with like the basic GCSE content. So you got displacement time graph. We know that the gradient gives us velocity. This is a linear gradient, so we know that the velocity is constant or uniform velocity. And it would be a object to be accelerating if it was curved on an exponential graph. The same with velocity time graphs. Change in velocity over change in time gives us acceleration. Again, here we have a linear graph, so we see that as uniform acceleration. If we now just look at a bit more complex level, we can use it to apply it to a quadratic, but we see displacement as a function of time. Over here, we have a quadratic. However, it can also be a cubic, a quadratic, it just depends on the graph. And as we saw before, the velocity is the gradient of a displacement time graph. So the exact same thing applies here, where the tangent in this case is the velocity. Now we could use our old GCSE methods to work out by estimating, roughly where the tangent is. Or we could use calculus to work out and be more accurate. We know that dy over dx is the gradient function of any graph. Therefore, differentiating displacement against time, we can see that we'll get velocity as well. If we now apply the same concept to the velocity time graph, we can again see that the tangent is the acceleration. So if we use the gradient function, we could work out what acceleration is. So that's the basic of using calculus and kinematics together. If you were to summarize it, we would just say that differentiating displacement against time gives us velocity, and differentiating velocity against time gives us acceleration. Now, if we work backwards and find the area of these graphs with integration, we would get the opposite. So we'll get velocity here with the integral of acceleration, and the integral of velocity will give us displacement. We'll look at something a little bit more complex now, force, mass, and acceleration. Acceleration is, of course, the derivative of velocity. And if we now just times by that change in time, we'll get two differential equations. Now we can integrate both sides. The left side we integrate by time to give us impulse, and the right side we integrate by velocity to give us mass times change in velocity, given that mass is a constant. Now we know that mass times change in velocity gives us momentum, so this proves the relationship between F equals ma and change in momentum. If we now look at the impulse-momentum relationship, we know that J, which is impulse, is equal to change in momentum. So now this basically means that every moving object must have momentum if there's a net force applied, which is basically Newton's second law, F equals ma. However, if there's no net force applied on an object, then there's no change in velocity, hence there's no change in momentum. I'd like to just consider one more thing. If we have force as a function of time, if we draw the graph and calculate its area, we will get impulse, which is the same as integrating the function of force against time. Now we showed this concept before when we were deriving the equation. We saw that if we integrate force against time, we get impulse.